Okay, should be live now. Let's get the notification out. Welcome one, welcome all. Okay. Excuse me. Cool. Notification sent. And people should be good to start strolling in. Let's see if the stream actually looks correct. Okay, Stream Manager says it is running. Okay, and that I have a bitrate. I like how it's just a flat line. My bitrate says I'm offline. That doesn't seem right. Come on, Twitch, stop being silly. It's probably just delayed. Let's double check this is all working. Okay, yeah, I can see my own stream. Cool. Welcome one, welcome all. Feel free to say hello in the chat if you're here and watching. Today we're going to be going over a bit of a ridiculous performance deep dive that I did recently. It's not that ridiculous. But it's on a topic that I've always been quite a big fan of, which is the performance of dictionary-like data structures. And so when it comes to the dictionary, I have already displayed what is like the most traditional, what you'll learn in your CS classes, dictionary, or in this case, it's a set implementation. Now, for simplicity purposes, I made my hash function just be modulus to make it something that you can do in your head. And so this is a extremely tiny hash set that has 8 main elements across it, excuse me. And so, you know, this is your classic thing that you'll find in a computer science class. And so fundamentally what we're looking at here when we see this is something where these are just 8 different buckets in a flat array. You get an item. So like, you know, if we're saying, hey, is 35 in this, we take 35, we modulo it by 8, which happens to be 3. With that 3 right there, it's pretty simple. We just go to the, I guess, 4th bucket, but index 3. And we just start checking items to see if 35 happens to be here. And so in this traditional set, we check is 91 equal to 35. Oh, no, it's not. What a surprise. Then we have a pointer. We chase this pointer. We go find 3. We're like, oh, is 3 equal to 35? Ah, still not. And then we just keep repeating this. Chase the pointer. Is 81 equal to 3? Or equal to 35? No, it's not. Chase the pointer again. Is 27 equal to 35? And again, no, it's not. At this point, we've run out of pointers, and we can say 35 is not in this hash set. And this implementation, while being a great exercise to teach students, is a pretty terrible implementation. And mainly that's because in academia, we like to use linked lists a lot, too much, because linked lists are like the worst thing ever for a computer. I don't know if you've actually used a real computer, but they don't like linked lists. They actually just have this one array that they like to call memory, and a linked list built in an array is just jumping around randomly. And so this is exceptionally cache unfriendly. Realistically, when running this, what will happen is you will have this main array in some level of cache. You know, if it's big enough, it'll be in L2 or L3. If it's large enough, it'll actually just be in main memory, but with chunks of it loaded into the main cache. And so, you know, with a smaller one, we'll say, okay, this array right here is completely in your L1 cache. That's totally fine. This first lookup is basically free. It's quick. You grab the index and, you know, and if you're lucky and it happens to be an empty cell or it happens to be the matching element you want, you're done. And that's quite nice. That said, there's a very good chance that you won't be lucky. And immediately you'll be following pointers. And for each of these pointers, you're probably getting a cold cache, right? Like you're probably going to a location that's not in cache and is in main memory. Or if it's in cache, it's in a farther up cache that's going to take more time. And so for each of these different jumps that you do, you might be waiting 100, 200, 300 cycles even, in like the worst case, depending on your machine. If you're lucky, it could be as fast as 4 cycles. right? That tends to be about the time of a hit in the smallest L1 cache. But nonetheless, this is just a terrible idea for anything performance. And so obviously in Rock, we don't generate the traditional hash set. And so I'm going to go through and kind of walk over some of the ideas about how this can be made better. And so the first one is pretty obvious. And we're like, okay, well, we just said that being spread out across memory is bad. So what if we just put everything in a flat list? Like, it's just guaranteed to be flat. And so this is our next example, the naive flat hash set. And so this just has the most basic idea to it. What we're going to do is we're going to just, whenever there's a element that we need to place, if it lands in the wrong spot. Oh, hey, Luke, how's it going? So if we have an element that lands in the wrong spot with the naive flat hash set, oh boy, I'm going to be saying hash set a lot today. I should have practiced that beforehand. But with the naive flat version, right? So when this 27 came in to get inserted, it actually wanted to land in the index where 91 is right here. It realized that was full, and so it just kind of went to the next one. And, you know, this is kind of reasonable. Now if I want to go look up 27, it's pretty simple. We come to this 91 slot, we're like, this is already occupied. Maybe we just got pushed to the next slot. We go to the next slot over, and we're like, oh wow, look at that, 27. And so the base idea of this is actually not too bad. Look at this. This is nice and cache friendly. These are all right next to each other. And you're still distributing. So like, what's the big pain point? And so the big pain point comes in when you have something like what happened here with poor 83. So 83 right here, when it was inserted, it wanted to be put all the way up here where this 3 was. But instead of doing that, well, the next slot was full, and 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 so it got placed all the way over here. And so now we're going to do that same key lookup. If we go and say, hey, I want to look up, is 35 in this set right now? Well, 35 modulo 16 is 3, so we start in this 3 bucket, and so we compare, and we're like, is this a 35? Nope. Is this a 35? Nope. Is this a 35? Is this a 35? We keep going, and we have to go all the way past this 9 here until we get to this empty slot. So we don't know 35, like whether or not 35 is in the set until we get all the way over here to this 10 slot. And so this is just a terrible failing of a naive flat hash set. You will get these ginormous chains that end up happening, that end up pooling together, and then you're just doing linear search. And like, why are you even using a hash set at that point, right? Like, if you're just constantly doing all of these linear searches, what happened to your beautiful O of 1 lookups and inserts and different things of that nature, you know? And now these linear searches shouldn't get ridiculously long, except on like really bad cases. But you don't really want your hash set to have, like, you want it to minimize the bad cases for your hash set. And so this is just a brutal performance hit, and why the naive flat hash set is just a pretty bad idea. Like, at least you're doing a linear scan over like a subset of the data, and so like this is, you know, maybe a smarter version of just doing a flat list with lookups, but it just devolves into a linear scan so often that it's not worth it. And so the next idea, to be a little bit better than this, is a thing called quadratic probing. And so when we get to quadratic probing, the big idea about it is that we're not just going to jump around the hash set linearly, but we're going to be a little bit smarter with how we jump around. And so in being smarter with how we jump around, the core idea is just that we like change our distance. You know, maybe the first jump's 1, then the next is 2, then the next one is 3 elements, right? As can be seen here. And so there's a lot of options for exactly how you go about doing this. The fundamental important piece, though, is that like these numbers will always be the same, right? Like it'll always go jump 1, jump 2, jump 3, jump 7, whatever order it goes. You know, if it's just jump 1 more each time, or if it's double the jump each time. Excuse me. It's also quite important that when we're doing this, that these numbers jump in a way such that you will eventually visit the entire set. You know, and so you can't just do jump 2, jump 4, jump 6, jump 8. You'll miss all the odd elements in the set, and that will be quite problematic and ruin your performance. The important thing about this design, right? And so like, you can see with 27 and 91, like we saw in the last example, they're still actually exactly the same, more or less. 27 wanted to be in the slot where 91 was. It couldn't be there, so it just went to the next one. But now with 83, we have a little bit of a different change. It wanted to be where the 3 was, so then it looked at the next slot. That was still full. So then it looked at 2 slots away. That was still full. Then it looked at 3 slots away. And that's where it finally got to land. Now you can notice, because of these jumps are getting bigger and bigger, we are losing a little bit of our cache friendliness, right? If this next jump is 4 and then whatever, this is worse than a linear scan in terms of cache friendliness, because you are jumping around. But the big thing with jumping around is there's 2 main gains. One, you're less likely to run into a situation like this, where some big pool of elements just kind of totally ruins your performance. This is 5 jumps just to check something, and to check if something's not there, we have to go, all the way to slot 10 here. That's, a terrible amount of extra checking for no good reason. And so with quadratic probing, we now only have 3 jumps instead of those 5 jumps. And so that's a little bit better for finding out if 81 was in the set, for example. And the other important thing about it is when we're asking, is 35 in the set, this now becomes a little bit better, right? We check here, we jump to the next, we check here, we jump, we check, we jump, we check. Then we would jump over to this 4 away here, this empty slot, and that's when we're done. And so this is a functional hash map now. You could write this and run it in production, and it wouldn't be terrible. It wouldn't be very good either compared to modern standards. But at least now there's a really strong baseline that we're working with here. Things are distributed well. You're likely to have a very well even mapping. Now, of course, you need a good hash function. That is fundamental. Again, just using modulus as the hash function is why these examples can be so terrible. But the question is, how can we make this better? I'd really prefer if I didn't have to jump around memory all the time, right? Preferably, it's a CPU. I would love it if I could have some sort of like super compact, tight data structure that I can just like iterate through linearly or something. Or even if I jump around in it, I jump to it, but then it does some sort of like local work that's basically super fast. And that's where we kind of get into some of the now starting to be much fancier, much more useful implementations of a hash map. And so what we're jumping to now is definitely a more complicated hash map. This is the Abseil flat hash map, at least a very rough approximation of it. For those of you who don't know, Abseil is the standard library, essentially, of Google code. So this map is probably one of the most used maps in the entire world, given that all of Google uses it. Right? Well, all of C++ in Google, but nonetheless, all of the high performance code in Google that really matters uses it. And so this is a very well designed map, just simplified a little bit for the purposes of displaying here. And so the 2 big features that the Abseil flat hash map has essentially are grouping and metadata. So what you'll notice now, instead of hashing into each of these buckets, or each of these cells individually, I've grouped them into buckets of 4. And so here's the first block of 4. Anything that hashes modulo 4 to 0 goes here. Anything modulo 1 goes in bucket 2, modulo 2 goes in bucket 3, or modulo 2 goes in bucket 2, modulo 3 goes in bucket 3, etc. And so that's kind of the base state here, is we've now grouped things together. And so what does this grouping really get us? It's a little weird to say, right? Like, oh, all of these things over here, they go into bucket 3. And so now we have like this list of things that go in bucket 3. You're like, oh, that's worse. Now you're just basically going to just always be linear scanning this bucket. Wouldn't it be better if there's a chance that you just hit it on the first try and you were done? And you would be correct that if that was the only thing they did, this actually wouldn't be that great. It'd be okay, but it still would not be a very good optimization. And so the very important thing they do is they add metadata. And this metadata, each of these is very densely packed, very tight. And normally their blocks, just to clarify, are in 8 or 16, preferably 16 on any sort of standard like Intel or AMD machine. And this is really important, is that when they look at this metadata, because it's so densely packed, they actually deal with an entire block of metadata at once. And so they're able to check one entire block of metadata at once when they're looking at it. And so there's a chance that they'll check a block of metadata and then never look at this big list, never jump around in memory to this less densely packed stuff. And so what is the metadata? In reality, it's part of the hash, but given we're just doing modulus as the hash, that didn't work out. So I decided to switch up the metadata. And so in our case, I made the metadata the highest digit, essentially, of each bucket. And so you can see, well, this is, or I guess it's the tens place is probably the best way to put it. So 4 with a 0 in the tens place, 32 with a 3 in the tens place, 27 with a 2 in the tens place. 1 and 5 both have 0 in the tens place. Here we have a 6 in the tens place, a 2 in the tens place. And so fundamentally, what will end up happening is when we ask the question, is 35 in this set, right? We want to check. So we say, okay, well, 35, it goes into bucket 3 again, because 35 modulo 4 is 3. And so, we say, okay, we're going to start by checking the metadata for bucket 3. And we're going to say, well, 35's metadata should be a 3. Its tens place value is 3. And so we say, hey, is any of the metadata here a 3? And the answer is no. And so immediately we go and say, hey, 33, it is just like not in this bucket at all. There are no 3s to be seen here whatsoever. It literally, there can't be, 35. There can't be a 35 here. It's impossible. And so what does that mean? Well, we also know from this that the bucket is full. We checked that as well. And since the bucket's full and 35 isn't here, we then follow the same quadratic probing we mentioned before. And in this case, that's this line shooting out over here and around to 27 landing over here. That's where it goes next. It goes 1 bucket away, and then again it would go 2 next, and then it would go 3 next. But in this case, it goes 1 bucket away to this very first bucket here. It loops the hash map and goes to this first bucket here. And so this first bucket here, we then say, hey, do any of these have a metadata of 3? And look at that. There is one. There's a metadata of 3 right here. So then we go and check it. And we say, hey, is this 35? And we find out, no, it is not. This is 32. And so with that, to figure out if 35 is in this set, we basically do one operation here on this side for the end metadata. We do one operation here on this metadata, and then we do one check here. And now we know that 35 is not in this set because there's an empty bucket at the end of this, or an empty cell at the end of this, which means that there's no way that it could be anywhere else. If there was a 35, it would have been placed in that empty cell right there. And so with essentially 3 checks, we have figured out that there's no 35 in this set. And most of those checks would actually be going through this very densely packed metadata at the bottom, with very few times that we actually have to go and load data to get keys. And so because of that, this is very cache friendly. You stay in your metadata, and occasionally you do have to jump out and go into the real data, but at least you're loading a big chunk of it at once so that you can deal with multiple hits at the same time, right? If both this cell and this cell, both of these 2 cells here were both 30 somethings, we would have loaded them both if we saw a 3 here for both of them. And so this is essentially how the Abseil flat hash set works. This is kind of what runs the Google world in terms of performance. So with a hash set, you always have a fixed amount of memory, essentially. Apparently, noob is a not permitted term by default. Interesting. I had to approve that message. Brought to you by auto moderation. But anyways, so hash sets almost always have a fixed amount of memory, and this is just because to begin with, you have to do this bucketing, right? Even if we go all the way back to this first implementation here, we have to be able to say, oh, modulus, this item goes into the slot modulus 9, right? And so even for this flat map here, we need to have this backing array of data for it to work out. And this is just a strict requirement because we don't want to be in pointer hell. Because pointers are slow and they just ruin performance. You know, I don't want to wait 400 cycles of loading just to figure out 35 isn't in this set. I would much rather be down in the world down here where this is already in cache. I do 2 quick little checks, then I maybe spend like, you know, 100 cycles if this isn't in cache at all, maybe. But in reality, this is probably in one of the caches somewhere, so it's probably a bit faster than that. Unlike the random pointer, because you're probably accessing your hash map a lot. So a lot of this is probably, if not in your L1 cache, probably in your L2 cache. And so then when you do this check and you figure out that 35 is not in the set, you know, that all ran extremely fast, with as few cache misses as possible. And that's what makes this great. The Abseil flat hash set, it's actually one of the best hash sets at finding out if something is not in your data. That is actually one of its big skills, because if something's not in your data, you might literally only look at the metadata and never look at the real data. And so you're going through this super dense stuff. You're checking in reality 16 elements at a time. So why is accessing the metadata fast? So there are 2 important things about the metadata. One, each of these things in the metadata here would only actually be a byte. So what it actually stores of metadata is a byte per element. And so technically 8 of these fit per like integer size. So it's very, very densely packed. And then the other thing is, because it's accessed so often and it's pretty small, you know, being made out of bytes, 1 byte per element, it almost always is in your L1 cache, right? And then lastly, because it's one linear array of memory, you know, when you say fetch this element right here, right? If you tell it to fetch this first element here, the CPU will automatically fetch a bunch of other elements for you, because it just assumes you're going to use the things that are in linear memory going forward, right? And so extremely naturally, like this data just will fall close to the CPU all the way in the L1 cache, unless you have such a gigantic map that it just can't all fit in the L1 cache, in which case as much of it as possible will be in the L1 cache. Now, this data up here is likely to be a bit colder, right? If you're always using the metadata, and that's in your L1 cache, maybe that means a lot of the real data is in the L2. And so you're more likely to have some potential cache hits, or cache misses with this. But you will absolutely never have the case of going to a totally random pointer. These are 2 linear arrays. And actually, in reality, the metadata array, right after it ends, is where the data array starts. And so there are 2 arrays that are actually attached at the hip. They're in one really big allocation. And so yeah, metadata being very tightly packed, being checked in practice 16 elements at a time instead of 1 element at a time, and only having false positives. I think it's 1 in 250 checks will have a false positive that will require you to go to a bucket and actually look up data. So only on average 1 in 250 of these like lookups or so. Well, no, because you're looking at 16 elements at a time. So divide that by 16. So I guess still 1 in 16 of these, you do have to load some sort of element. So it does happen, right, that you are falling back onto this main array. But it's just so much more likely that whenever you look at this main array, you know, I mean, I already checked, right? When you looked at this, I already checked that it starts with a 3. So probably there's a really high chance that's a 35. It ended up being a 32 in this case, but you know, the metadata makes it much more likely that it was like worth it to go check out that data. That said, not all maps do this, where they split out the metadata into a nice dense packed structure. Though it is a good idea and it does add a lot of performance, it doesn't always work out well, depending on what other trade-offs you want with the map. And so in our case, we used to be implemented in a way that was basically a very poor man's implementation of this. The biggest reason it was a poor man's implementation of the Abseil flat hash set is that we don't have all of the SIMD and allocation tricks and whatnot that the Abseil flat hash set has. And on top of that, I never dealt with removing all of the possible ref counts that were in there. That's not true. I removed as many as I could, but we actually need to do some compiler changes before all of them can be removed. And ref counts in a hot loop are really bad for performance, to say the least. And so nonetheless, all of this, though it is a nice implementation, it didn't really work out for Rock. The other important thing about this and why we couldn't use it for Rock, and I should have made an extra visualization for this, but if you notice, this data is in like a totally garbage random order. Like, tell me, like, why is the one right over here, and why is it not there instead of there with the 5? Like, why aren't these in the opposite order? And the answer is, well, it just happened to be that way based on how items got inserted and how the hash worked. And that's a problem for Rock. If we were to just use an Abseil flat hash map, someone could use a dictionary as a way to generate randomness. And that would break all of our fun, referential transparency. If someone can make a dictionary, throw some elements in it, and then get a random order from it, they suddenly can just generate random numbers by using our dictionary implementation. And so we actually couldn't just use an Abseil flat hash map. What we really used was something that's called essentially an index map. And let me just pull this up, because I didn't make a slide for it, and I hope they have an image of it. So there's this thing called an index map, and they don't have any pretty images. Disappointing index map. You should at least have like one image of this. Let's see if their repo has one. Maybe? No. Okay. But anyways, the idea of an index map is that instead of storing the data here, right, this is directly storing the data, what you would store there is an index into another array. And that array is just a flat array of your data, right? So it's kind of like you build the list as if I was just calling list.append a bunch of times, right? You build that list, but then you also store all these indexes into it. And so now your lookup is basically check the metadata, jump over here, say, hey, I'm pretty sure this is a match. It's in index 5. Like, these would be indices instead. Then you go to the final list on index 5 and use that. And the important note here is there's now an extra jump. You go from metadata to your index list to your actual data. And so it throws in an extra jump. And so Rock's version has that extra jump built in. And that actually tends to be quite bad for performance. It's one of the biggest reasons that our old version of the map was slow, is we had this extra jump. And so eventually I will get to like what our implementation is now and how we deal with that. But to do that, we actually have to go back a little bit. Go all the way back to this fun guy, the naive flat hash set. So the big thing with the naive flat hash set is that it has this really big problem where it turns into a linear scan, and linear scans suck, right? I don't want to have to check 7 elements to find if an element is there in a hash map that has, like, right, this, if I want to check 35 isn't here, I have to go through and check 7 of the elements. Okay, this map only has, like, what, 15, not even 15 elements. What is this? This map only has 12 elements, and I have to check 7 of them. That's just terrible. Like, I might as well do a linear scan at this point. Like, I might as well just have an array and do a linear scan if I'm going to be checking 7 out of the 12 elements anyway, right? And this continues to happen as you go at bigger scales, right? The map grows larger, and now this chain of linear scan keeps getting larger as well. And so the question is, hey, instead of trying to do this metadata and quadratic probing and other tricks, linear scans are actually kind of nice because they're super duper cache friendly. So like, what if we still do the linear scan, but we just try to not let this happen? Okay? Like, let's not make it where I have to scan all the way over here. And so this leads to a different branch in the world, to a tool called Robinhood hashing. And this is named after the legendary character Robin Hood, who, stole from the rich and gave to the poor and whatnot. And that is like actually what this is named after. But nonetheless, so if you notice, there's now metadata here, and this metadata doesn't need to be attached here. It could be in a separate list, just like we saw with the Abseil flat hash map. That would be fine. For our cases, it will be attached, and that is actually how the Rock implementation works. It is attached. But nonetheless, we now store this extra piece of data for every index, or for every element. And this piece of data is essentially how wealthy one of these elements is. And so how do we measure wealth in this case? Well, wealth is how close you live to where you wanted to live. So all of these elements, this is to be fair, just to clarify, is the exact same list we saw over here. I just annotated it. It is not actually yet a truly valid Robinhood flat hash set, okay? And I'll explain that in a minute. But right now, it's just to show how poor everybody is, or rich. And so you can see all of these elements with 0 under them, they're exactly where they want to be. They are the kings, they are super wealthy, they are rich, they are happy. And actually, almost all of these elements are quite happy with where they are. And then there's 83. 83 is the poor peasant outside in the cold, it's raining on him. He is 5 whole slots away from where he wants to be. And so, this is where Robinhood hashing comes in and says, hey, you know, 83 may be really poor, but maybe we can distribute the wealth a little bit. And then 83 won't be so poor, but also, you know, all of these other elements before 83 over here, 4, 5, 22, 7, maybe they'll be a little less rich than they are right now. And so, you know, just to clarify, right? So this is 0, right? Because it's exactly where it wants to be. If 83 was in this slot, it would be a 1. Then it would be a 2 here, a 3 here, a 4 here. And because it's all the way over here, 83 is a 5. And so now we're going to make this a valid Robinhood flat hash set. So what does it take to actually make this useful and correct? And as I said, we're going to steal from the rich and give to the poor. That is actually how this map works. And so when we put in 83, instead of putting it all the way down over here, we move it over and we say, oh man, 83, you're actually a 1 now. You're kind of poor. You're poorer than 4 here. So let's kick 4 out of its house. And so then we kick 4 out of its house to its neighbor's house. And then 4, we're like, oh, you're actually poorer than 5 now. So you know what? 4, you get to kick out 5. 5, you go to the next house over, okay? And then 5, again, is poorer. And so it does this chain of updates. And so during the insert, it can have a little bit of a cost involved in it, but generally it's amortized to not actually be a big deal. And again, it's just a linear scan to do this. And so it's as performant as it can be, very cache friendly. And so now we have this case where we basically just kicked out, you know, 4 different people from their homes in order to give 83 a nicer home. And so now we've stolen from the rich, and now everybody is a little poorer, right? They're all 1s now, but now 83 is also a 1 instead of a 5. And so now we've redistributed the wealth. And so what does this mean? So before in the linear scan case, right, to check if 35 was in the set, we had to do 1, 2, 3, 4, 5, 6, 7 checks, and then we ran into the empty slot. And that's when we knew 35 wasn't there. So with this Robinhood hashing though, how many checks do we actually need to do? So we take 35, we bring it to the slot, we compare it to 3, and we say, oh, not equal. Okay, so there's 1 failed check. When it's not equal, we move it over 1 house, we move it to the next house over, and we increase its number, because now it's 1 slot away from where it wants to live. And we say, oh, well, I'm 1 slot away from where I want to live. You're also 1 slot away from where you want to live. So maybe that means that I belong in your slot, right? Maybe that means there's a 35 right here. And so we check and we say, oh no, 83, that's not equal to 35. Okay, fair enough. And so 35 gets kicked. Okay, maybe 35, you're actually in the 3rd house. And so that's 2 is your value here, right? And so now it goes and we say 2, wait, but this person's only 1 house away from where they want to live. That person cannot be 35, because if it was 35, they'd be 2 houses away from where they want to live. And immediately at this point, we're done. With just this 1, 2, and then a little metadata check right here, we're done. We know 35 is not in this set. And so instead of this like 7 element, really inconvenient linear scan, we've now greatly reduced the amount of scanning that's ever needed to be done with this dictionary. And so now we have a table that actually is pretty solid, right? We have a lot of properties that are still pretty good, you know. We're reducing how often we, like we still have the linear scan and its issues, but honestly, a short linear scan is pretty nice. And so we just look up directly the bucket we want, and we do this short linear scan. And as I mentioned before, there are a number of hash maps that are much closer to the Abseil flat hash map, where essentially what they do is they take all this metadata here, all this stuff here, and they just densely pack it into its own side table. And so then you still have the same thing. It's almost exactly identical to the Abseil flat hash map, but instead of doing this quadratic probing and whatnot, you end up doing these checks for, you know, Robinhood and how close you are from the home you want to be. And so this keeps with linear scans as opposed to quadratic probing. And quadratic probing eventually gets big enough jumps that it's actually not great for cache performance. And so this tends to have better cache friendliness, especially if you split off the metadata into its own structure. such that it's super densely packed. That said, in our case, we don't. And that's because the index map constraint that we talked about before. And so next, we're going to the full deal. This is actually what Rock now is about to implement. It's this PR that I need to fix one little thing on. But now we get to the real deal. What is it that we're actually trying to implement? And what gains do we get for it? And it's a little bit more complex. I won't lie about that. Hopefully this is still mostly readable and not too overlapped. And so as I said, Rock uses an index map, which means we have one array here that is literally just as if I just did list append every time I inserted an element, right? This is just the elements in the order they happen to get inserted, right? Here are all the elements. There's our 83 that got inserted last. Oh, you can't see that. He's right under the thing. There's the 83 that got inserted last. And so he had a really bad time in some of the other versions of the set that I was showing off. But fundamentally, this is just an arbitrary insert order that I picked. And all the elements just got inserted, and that's where they landed. And so it's just a flat list. You could take this list and use it as a regular list, right? But now the question is, how do we take this list and still get the good performance? And so this is that same Robin Hood map that we saw before, but instead with indices. So if you look at this, I added all the lines, right? Element 0 landed here. And so we don't know what element 0 is. It happens that element 0 ended up being 5, right? And so you don't actually know what the element is in this separate map here. You just know where it is and a little bit of metadata. And if you notice this bottom line here is actually the exact same thing that we saw above. That's the same line right here of how rich or poor every element is, right? And the exact same thing happened with, 83 kicking a bunch of people out of their houses, right? So that's the exact same thing right here. We have this bottom line here, and you can see all of these different slots are one poorer than they want to be. And you can see that index 11 here, if you follow it over, is where 83 is. And so now if you notice the second line here, the astute among you might have noticed that this is actually the same metadata I showed you in the Abseil flat hash map. This is that, what is the tens place for each of these digits, right? What is the tens place, essentially? And so in this case, you can see, well, 83 has a tens place of 8. And so again, if you follow that index over here, you see that there. So the question again turns out like, okay, what do we gain from this? And so one thing I can immediately tell you is if you do a index map type data structure where you have pointers to the final array and you build it on an Abseil flat hash set, you have 2 pointer jumps to get an element at a minimum, right? You have to follow into the final array. Like you go from metadata to data to then the final actual element. And in this case, because we store things together, we only ever have this 1 pointer jump here, right? We only ever go from, we go into the metadata and then we go from metadata to the final index map. And cutting out that 1 pointer jump is actually quite important for performance. And that's actually probably the biggest reason why this map is better for us than the Abseil flat hash map. But nonetheless, we can go through a lookup again in this set just to point out how it works. And it's almost the same as what we saw before. Note how last time I had a little thing that was 35 and 0. Instead, we're only looking at the metadata this time as opposed to the full data. And so this is 3 and 0. We're saying, hey, this guy starts with a 3 or has a 3 in the tens place, and it has it's currently, this is the slot it wants to live in, right? It wants to be in this slot right here. It goes modulus into the 3 bucket. And so we compare right here and we say, oh, hey, same bucket. Yes, you could be someone I want. That could be me. But then we say, oh no, you don't start with a 3. Nope, that can't be me. We move this over 1. And what we do is we just increment that value again. Now we're 1 slot away from where we want to be. So again, we do a second metadata check and we say, well, oh, this could be right. You're one slot away from where you want to be. I'm one slot away from where I want to be. Oh, but you start with an 8. Nope, that's not right. Okay, and so we go our 3rd slot away. And again, just like last time, we now have a 2 here. 2 is greater than 1, and so now we know, hey, 35 can't be in this set. And so we just did this light little scan through the metadata, and we're done. That's everything. Now, let's just imagine for a second that instead of 83, this actually was 35 here. I can't type. And so that means this metadata here is now a 3, right? And so what would happen in this case, now we actually do have 35 in the set, is again, we start over here with 0 and say, oh, nope, you don't have the right metadata. Can't be me, right? Can't be the right element. We then move over 1. We increment this to 1. And now when we compare these two, we say, oh, wait, look at that. The metadata is actually equal. And only in the case where the metadata is equal, we then actually fetch this pointer. And that can have a solid cost, right? Index maps, this is the big cost of them, is that you have this extra fetch here, and you don't know whether or not that'll be in cache. A lot of times, maps are small enough that that will happily be in cache. The index map author, actually, they took their map and replaced all of the maps in Rust's compiler with it, and they found that the performance was almost identical on average. Like, of course, some cases were a little slower, some cases were a little faster, but on average, the performance was almost identical. And that's just a point that even with this extra jump and cost here, it can still be faster, especially because now you have this list that you can use and that has a linear scan that just works. But nonetheless, so we get here and we say, hey, look, our metadata matches. Only then do we load element 11. And in this case, we'd say, hey, now we made element 11 35. And so at this point, 35 is in the set. And so that would be a proper check. And so this is essentially what I just implemented, was this, but in Rock. And currently the performance is pretty solid. Overall, I've only done a little bit of benchmarking, but enough to feel pretty confident about it. The new map is 1.5 to 3 times faster than the current one in Rock. And it still has room to improve. In fact, it's still 2 to 4 times slower than the C++ version of the map. The biggest cost by far is the fact that we have ref counts that shouldn't be there that we need to remove. We need to write an extra compiler optimization for this. It just currently doesn't exist. Oh wow, my camera is very bright right now. Interesting. Okay, whatever. Doesn't matter. But anyways, so we have to write an optimization to remove some of these ref counts. Once these ref counts are removed, I think we'll be roughly in the range of 1.5 to 2.5 times slower than the C++ version, which is still not really where I want to be. That's definitely slow. And so like there's definitely room to improve there, and that'll be really fine-tuned tweaking. Like, you know, obviously the brain not working for a second. Sorry. Obviously, the C++ version was written in a very performant way, right? And the person really was careful about everything they did. And even though I'm copying them, Rock and needing to be written in a pure functional manner makes some of that stuff harder. And then also some of the like cases where I've used closures or things of that nature might actually hurt performance as well. It definitely is hard to perfectly match C++ performance in Rock, at least as things currently stand. 1 for ref counts, and then 2 for loops that like you would have just written a densely packed for loop with some variables that it's referencing that now is like a closure with recursion or whatever. And so there are some cases that need to be touched up and worked on. I definitely want to get this really close. I want to have this in the 1 to 1.5 times, if not like almost identical performance. There are also some cases where we're using like checked arithmetic and extra checks on size to make sure we're not going outside of bounds and things like that. We have like some extra safety checks and things like that that the C++ map doesn't have. Nonetheless, to say, I think this is a pretty reasonable spot. I want to do some more testing also of Go, because I think they're a pretty good language to see what a reasonably fast map implementation is. I've only done preliminary tests, just a single preliminary test. I need to port more benchmarks. But in that preliminary test, Go was really slow. And so it may be the case that Rock's dictionary is actually already faster than Go's, but I'm nowhere near confident in claiming that yet because there's too much stuff for me to test before I'm really convinced of that. Is fuzzing important and useful for testing a new implementation? I think fuzzing would be 100% be a great add, right? I would love to fuzz this code. Do a lot of random inserts of randomly different types, and really drill into it to figure out, if it randomly eats elements or if it suddenly, can't find something or didn't delete something correctly, right? We do have a test suite, but it's pretty small, right? It's just a couple of expects and a few other tests. It's enough to feel at least okay with the map, but like it totally could have bugs in it that randomly break things. And so I definitely would like to do some fuzzing of it or something else to really battery test it. Would have to think how I would go about doing that, what the correct way to do that is, so that you actually get a reasonably looking use and then are also able to verify what the correct elements were supposed to be. Excuse me. But yeah, I think that would definitely be really good to do. I just haven't spent any time on that yet. I mean, this implementation is totally fresh, as I've said. I finished writing it yesterday or 2 days ago, whatever. I think some point yesterday. That sounds right. But yeah, so that's the overview of how to get a decently fast hash map, especially while preserving insertion order. And I just want to point out right now that, I didn't do any of this work or research in how to design these really fast maps. I've always been interested in it, and I've always followed along with people that do spend their time building these crazy things, and listening to talks and reading their documentation and whatnot. And so, like, I have ideas on, like, how to write a reasonably fast set, even if I didn't have an implementation sitting in front of me. But, like, fundamentally, I think his name is Martin Onkler? Onkerl? I don't know how to say that. I always say Onkler, but I don't think that's right looking at that name right now. The L is at the end. But nonetheless, this is his work and his implementation. He's written a few different very high performance hash maps. And I guess real quick, if I just pull one other thing up, do I have it up already? Yeah, I do. Well, something that'll get me to it pretty quick. This is also where I got some of my benchmarks that I've been porting from. So these are just some different map benchmarks to try. And I still need to port more of them, but I've ported a few of them to Rock. But nonetheless, he made this really great blog post, which is just hash map benchmarks, that tries tons of hashing algorithms, tons of hash map implementations, and compares them all. And his, on average, came out on top, but man, is it exceptionally close. Wait, why is this not loading correctly? What do I have going on here? Oh, this is the old one. I need to go to the new version. Did you link to that in? Okay, one more second. Yeah, there we go. So this is the new version, and you can see he seriously tested a huge set of maps. And so if we go all the way down to the results here, actually the table, he made this giant table where you can see exactly what every map is good or bad at. And it's compared against the fastest map at each thing, right? So like, for example, his map is exceptionally good at copying and iterating. Why is that? Well, if we go back to this picture, to iterate it, you just go across a totally flat array. That's about as high performance as you could get. And to copy it, you just, copy this array and make another set of metadata. In fact, you could literally just memcopy both of these and you would have a copy of it, right? Some maps that doesn't work out as well because you have all these pointers to follow and other problems of that sort. And you can also see, some of the things that it's less good at. It has a solid memory overhead in his benchmarks, right? And so this is with relatively small elements. And again, that's not surprising, right? If you go back to the implementation here, well, look at that. You have to store all these indices. Storing indices isn't free. But in our case, we have to do that anyways. So the memory overhead is really not a big deal because we need it. It's fundamental to Rock's dictionary type. But anyways, he goes over lots of different implementations, and all these different people make different trade-offs. Probably if I didn't have the constraints that Rock has with needing an index map, I think some of the EM hash maps are really good. I don't think they're index maps. I think they're a little bit slower to iterate. I think it varies. I think EM8 is and EM7 isn't. And then if we come down, all right, let me get rid of all of the... So if we come down a little bit, we can see, where is it? Abseil, SCA flat hash map. Where's my Abseil flat hash map? It should be here. Not that this is super readable, but here it is. And the Abseil flat hash map is like medium on everything, to pretty solid on everything, but really, really bad if you copy it or iterate over it. It's horribly slow compared to the other ones. And so, you know, it's rated probably worse than I would rate it because honestly, most people don't copy maps or iterate maps that often. They mostly use them for insert and find and things like that. And so I don't think that's a big issue. But anyways, that's the only real thing that really knocked down the performance of it. Otherwise, it's a very solid map. And the big thing, and probably why it's used at Google, is compared to all of the other maps here, it has a solid amount less overhead, and it's exceptionally good at telling when something's not in the map. And if you don't know, when it comes to computers and servers nowadays, oftentimes memory is more expensive than CPU. And so you'd rather, like Google would rather have a smaller hash map than have a faster one in many cases, because they literally are like running so heavily on memory. That said, it still is good at both. It's just not quite as good. If you walk, are you copying it? If you walk a hash map, you are not copying it. If you walk one of our hash maps, you're literally just walking the underlying array. That's all you're doing. It's the same as just list.walk on that array. And so it is, you know, going to grab the elements, and you will maybe be incrementing ref counts of elements or things of that nature, depending on what exactly you're doing. But fundamentally, you'll just be walking the underlying data. But yeah, that is a thing you have to be careful with in Rock. There are times when you may accidentally get into some ref count issues or getting into some cloning issues. And that could be expensive with a map. Not terrible, but not a good thing either. To be fair, to clone it, it's just 2 memcopies, right? It's memcopy this one list and memcopy this other list. But you know, that's not as nice as we'd like it to be. And that only happens if you have, like, you know, you're mutating a map in 2 different locations or something, right? And so, or like mutating it while having an immutable reference to it. And so reference counting is complicated in Rock. We do a lot of tricks to try and avoid that, but it is a sharp edge that can be hit. Okay, I feel like that's probably a pretty solid overview of maps. I've been diving into these way too much over the last week or so. I did that also right when I first implemented all of the map stuff. If you're using it in a recursive loop, is that copying? It depends on how it's used, right? So in general, because Rock does opportunistic mutation, if there's only one reference to a thing and you try to mutate it, you're just fine. Your only issue is if you are holding another reference and trying to mutate it. But generally, if you have like some sort of tail recursive function, you're probably updating the map, and then you're just like calling the next tail recursion of the function with the updated map. And so that will not copy. And so most of the time we have pretty solid performance trade-offs around that. Welcome. I can't read names on my thing. Fit Rioter. Nice name. Anyways, yeah, I think there are sharp edges with Rock currently, and a lot of them I think will go away as we work on more optimizations and ref count tricks and things like that. But for an average user, I think most people don't need to worry about it, and if you do need to worry about it, they're not really hard problems to fix. Most of the time, they're just little tweaks you can do to your code to fix them. Okay, would you look into the code you have written to know if you're copying, or do you have to be able to read llvm IR? So there's a few options here. Now that we have performance working, it's actually really easy. You run perf, Okay, you get a flame graph. And what you will see is that your flame graph is spending all of its time in memcopy. Right? In Rock, if you ever screw up something such that you're copying all the time, your flame graph will just say, hi, I've been spending all my time in memcopy. You know, I am literally just, every time I go to update this thing, I realize I have to copy it first, make a new copy, and then update it, right? And so it's really not hard to spot at all if you do any sort of performance benchmarking. And then, you know, because you have your call stack, you can figure out which dictionary or which list you're having this issue with. But I think it's a pretty easy performance thing to spot and to work on. That said, it does lead to some annoying code occasionally. So if I pop back over to my dictionary code here, and we go to files changed. Actually, let me pull it up over here. This will work better. Where is what I want to go to? Okay. Oh, gosh, did not mean to paste that. Okay. Okay, so if we go back to Rock here, and I can actually kill this for now. Okay. And we go into... Oh, I didn't check if I was on the right branch. We're not. Okay. Let me get over to the right branch real quick. Okay. And if we go into the dictionary file, so if I go into, I think what it's find key, is that what I named it? No. Oh, it's just find. Okay. If I go into this find implementation, does this have it? Actually, it doesn't. Okay, but one of these implementations farther down. Manual unrolling. Okay, here's an example. Okay, so this remove buckets function here, I needed to not copy data. And so one of the things that I had to make sure of is that, like, whenever I edit something, it stays unique and I don't have another copy of it. And so in general, oh yeah, now my camera's in a bad place compared to the other thing. Yeah, give me 1 second. Let's get that back over here. Okay, so in general, if you look at this code, you'll see this pattern where I have like data 0 here. And then as I go farther down, data 0 gets used a number of times, and right here I make it data 1. And then I use data 1 and it might become data 2 at some other point. And this is just me being very careful to make sure that when I use things, they're used until they die at a certain point and then they're gone. And so I don't hold a reference to them. And this ensures I don't get into any of those copying problems. And so that's just kind of like a how I have to do it currently in order to make sure I have performance. In the future, I'm hoping we add shadowing, because then it takes over the reference and I make sure I can never reference it again, right? Once I update data, it's done. You know, data is updated. There's no other version that I might accidentally reference, right? But if I wanted to ruin the performance of this application right here, right, I could simply go ahead and I could go right here, and I could just do anything with data 0. Like if I just do anything whatsoever with data 0 right now, like right after I update it and make data 1, this Rock app's performance will totally die. All Rock dictionaries will have the worst performance ever. And it's because every time you use the dictionary, you'll get to this location and it will copy the entire map in order to update it, because there's still a reference to it held. Most of the time things stay unique and everything works fine, but it is a sharp edge that you have to be careful of, and we're slowly improving the ways we can detect and make that work better. But this is definitely the big trade-off of Rock. We're doing opportunistic mutation. Essentially, when something is unique, you can mutate it, and if not, you must copy it. And the answer that you see from something like Rust is stuff is almost always unique, right? In Rust, you're constantly sending along borrowing and whatnot. And so that is just like a thing that shows how unique everything is. Also, going for why the at. So in Rock, we have a thing called opaque types. And if I go all the way back up here and I go to the definition of Dict, it is an opaque type, which is just specified by this little like colon equal thing. And so an opaque type has a hidden implementation. And so if you were to go use a dict in userland in Rock, right, if you're using a dictionary, you wouldn't be able to see all of this detail. All of this stuff in here will be hidden from you. You will have no way to access it except through methods that I expose on the dictionary class here. Or not class, dictionary type. And so you'll only be able to access it through things I expose. And so this oh my god, I can't type. @dict here is essentially how you create or pull data out of a dictionary type. Like how you get to the internal stuff. And since this is only available in this single file, no one else can pull data out of the dictionary type. No one else can get to its underlying implementation. It is hidden from everybody else. And so that's why there's an @ that you'll see all the time. Like it's all over this file whenever I'm building or pulling data out of the dictionary, right? So with this @ I can literally pull the data list out of the dictionary and return it. Okay. Have you ever benchmarked at what point it would be faster to use a persistent data structure? Okay, so I have benchmarked persistent data structures before. And my answer is, personally, I have never had a use where a persistent data structure would be faster than a regular dictionary. But I only use dictionaries in normal people ways and not in fancy ways. I can be a little less direct about that. Okay, so in reality, there is a specific use case for wherein a persistent data structure would be faster. And that's when you need many, many different views of the same data. And some of those views will mutate, some of them will stay the same, but you need all these different views. And so like if you had a dictionary where you were gonna make a bunch of copies of it and then edit some of them, that is where a persistent data structure is made for. That is where it works beautifully, right? So like if you were gonna take a dictionary, make 5 different copies of it and edit all of them slightly, persistent data structures do great for that. But in all other cases, they're pessimizing everything. And so almost always a persistent data structure, I think, is a bad idea. I get that some languages just have to because of how they're designed, and it does kind of work. But generally what a persistent data structure means is more pointers. And pointers are terrible for performance, right? Anytime you have to go look up randomly in memory, you're probably wasting 100 cycles. And so there is this trade-off of like, if you do truly need multiple copies of the same thing, and you're going to occasionally mutate some of them, yes, persistent data structures are important, right? And so for certain tree views of things where like you might edit subtrees and take out a subtree, do something with it, and then like replace it in a different thing, you may have cases where a persistent data structure would work out and be important. Also for certain things that are like literally so big that you have to store data on disk, where you like, you know, basically are like an SQL table or things like that, where you like might have a tree in memory and then data on disk. There might also be use cases for persistent data structures there, just because going to disk is so slow. But fundamentally speaking, persistent data structures will just always lose to regular data structures if you don't have the worst case situation. And the reason for that is, simply put, following pointers in your normal case, which is what persistent data structures have to do, is terrible for performance. But yeah, I mean, I could pull out some sort of, I'd have to find a good benchmark for it, like, because it's hard for me to think of a benchmark that like is good for a persistent data structure that like you'd even use a regular dictionary for, right? In reality, if you have a specific case for some sort of persistent data structure, you should just write that data structure and not use Rock's dictionary, right? Because the cases for it are just so slim and so specific. But yeah, I think I actually wrote an article about this at one point, but I'd have to go look it up. So we were talking about potentially doing that in Rock, and I was heavily against it. But yeah, as one APLer said that I quite agree with is, pointers are the sugar of programming. It's the unhealthy thing that is sprinkled everywhere that just destroys performance of your code, just like, you know, having too much sugar destroys your body. And I think that's a very true statement. Okay. Let's see. What do I want to do? Do I actually want to dive into like advent of code or fixing the one bug here? I can at least talk about the bug's actually really boring. So this is like ready to review except for one minor thing, and that like it calls num.floor, which calls floorf, because some reason Zig is generating a call to libc as opposed to just implementing floorf for us. And this silly call to libc is a doesn't exist if you don't compile with libc, and so I need to like implement it and replace it. And to be fair, this is a bug that's affecting all of Rock right now, apparently, in certain cases. But now that it's in the standard library, it hits everybody all the time, so I need to fix it if I want to merge this. I also learned that for whatever reason, so like, you know, most languages have a way to convert a float to an int, and it's even built into WASM. They have like a truncate command. And I use that float to int command as opposed to flooring the float because it should do the same thing. And on all of the different operating systems, it did the same thing. And on all of the different CPU architectures, it did the same thing. But for whatever reason on WASM, for whatever reason on WASM, it doesn't work quite correctly and it does the wrong thing. Oh no, it's because I'm silly. It's because floor, if you're negative, goes to the bigger or to the more negative number, doesn't it? No, it's just because I did a truncate. That's why. Truncate versus floor. I'm not very bright sometimes. Okay, anyways, that was a side tangent. So one option right now, if people are interested, is I need to port this code to Zig. Just port this implementation of floorf into Zig such that we can pull it in our standard library and stop depending on libc. Another thing I might do is advent of code, because I am 3 days behind now. I need to do some catch up. If people are interested in that. Otherwise, I do need to double check some work stuff and make sure that I can actually keep streaming today, because there's some chaos at work I've been dealing with. But if anybody has any preferences there, please feel free to like send a message here. See if someone actually finally replied to my pain at work. Yeah, Zigzet floor call calls libc. If you, I feel like it shouldn't. I don't. Maybe we're just linking in a stupid way, and that's why it's calling libc. I really feel like it shouldn't. Let me just pull that up real quick. So if I come here, I go to num.zig. So we have our bitcode here, and we have a floor c function or floor function here. I just changed it to not use floor, which is actually totally incorrect. But before, it was set up like this. Give me 1 second. Ignore my totally wrong comment because I don't know the definition of floor and thought of truncate. But if I go here and I put floor here, okay, which if you go to the definition of math.floor, it's just calling at floor. Okay, it's the same thing. I'm calling at floor here. If you run this on a Linux machine and you run it such that it doesn't link against libc, it will fail. And it will fail with, let's see if I can pull this up real quick. Right here, if I go to this failure here, we will see right here, can't find floorf. Where's the actual name? I know it's in here. Yeah, right there. Can't find floorf. I can also probably zoom in a bit. But right here, it is unable to find floorf, the symbol, because it wasn't emitted. Now, I'm betting if I let Zig do all of the linking, period, it would maybe figure out this floorf thing. But Zig is not doing all of the linking, and so it's not generating floorf for me. And so maybe there's something I just need to add to Zig build to tell it, hey, please generate floorf for me instead of assuming I'm linking against libc. Like maybe that's just something missing in our build.zig that I need to work on. Like maybe there's something I need to be throwing here to tell it that. Do we tell it we link libc? Let's just make sure we don't say something stupid. No, we don't. There's nothing in here saying libc that I see. Okay. But yeah. So I'm not sure why, but yeah, okay, cool. You know, it doesn't have anything talking about libc. So we don't tell it to link against libc, but its floor call is calling floorf by default, and it doesn't generate it. And so maybe there's something I can put here and say, hey, Zig, please generate all of these libc calls that you are making, or don't use libc calls, you know, generate everything. But if not, I just need to implement it manually in Zig and then set up all the linking for it. Yeah, so I'm not sure my exact plan there. I feel like going through, this is one of the things that's, Zig's build system is great, right? I love Zig's build system. I think it works wonderfully, but God, figuring that out is not. You like come over here, you go to what, we're on 0.11. Oh, actually, no, I like the new docs. They're prettier. But like you come in here and like there's no good docs. Instead, you're like digging through all of these build APIs and a million different flags here that you're not fully sure if you're allowed to set or if they're like automatically set when it's running because they're part of the data structure. And not to mention like a million different functions. Is Rust a good choice for a compiler project? I switched to it from C++ recently. Ooh, that's a good question. Personally, I think Rust is a fine choice. I think it's okay. I think ownership and borrowing is definitely helpful at times. I think that it catches a ton of correctness bugs that I would have failed to catch if I was using C++. That said, honestly, if I were to rewrite Rock's compiler, I would build it in Zig. But like that's for minor gains of certain specific annoyances I have with Rust. You know, slow compile times, not having control over allocators that are threaded through the application. That's a big one because for a compiler, a lot of times you want to arena allocate things or like make more fine-grained allocator decisions at certain points. And then honestly, even though the borrow checker does help with a lot of things, a compiler, I think in many cases is not too complex to deal with. And if you just have a simple defer and error defer, you can deal with most of the cases. No, I haven't used Zig in Anger nearly as much as I've used Rust in Anger. So, yeah, no, I'm not fully convinced whether or not that's a true statement there, that like I would actually enjoy Zig better if I could just like if I magically switched it out. But I would say like if I had to pick a language, you know, Zig would be my first, Rust would be my second, you know, and I would put them both way ahead of C++. In terms of it. And just to clarify, I work day in, day out working on compilers in C++. That is my life, actually. I work on compilers in C++ now daily. Mostly I work on proprietary stuff. Occasionally I touch llvm itself, but that's exceptionally rare. Like I interact with llvm all the time, but I don't normally directly work with it. Most of my work, though, is using mlir, and it kind of deals with a lot of the edges of C++ to make them nicer. But also, if you don't know mlir, I would not advise learning it to make a compiler. It's just too much. And it's a specific way of thinking and doing things that I don't think a lot of just people want to deal with. Even though as a compiler engineer, I think it's nice to have a standard of this sort and have a lot of people build off of it. I wouldn't just advise it to random people on the internet for sure. Yeah, that's definitely one of the things that is a pain point of mine. In fact, right now, for the last 2 weeks, I have been tracking down a single bug in our compiler. That's how bad C++ is sometimes. This is a bug that should not exist at all. And I still am not sure if it's a real bug or if it's some sort of weird optimization thing. So, yeah. C++, so much fun. Yeah, sum types are beautiful. Oh yeah, I forget that. Zig doesn't have nearly as nice of sum types. You know, I might have to take back my comment about that. If I play more with the sum types in Zig and compare them to Rust or like their enums, I might find that the sum types in Rust make me like their enums. Rust enums are beautiful. Okay, so like I might find that using Rust's enums would make it so nice that like I would not want to switch to Zig actually. Like if I switch to Zig and their enums their enum and tagged union story just doesn't feel as good, I very well might say actually Rust is the thing for me when it comes to compilers, because sum types are just wonderful when it comes to compiler development. You have to be careful of how you use them because it's really easy to make recursive sum types that then have pointers in them that are actually really slow and not the best way to do things. And so this is where it's kind of weird, is like, I want to use Rust sum types and have all this fun and different things, but at the same time, if I really care about performance, which I don't think most people working on compilers should, most people who are working on open source hobby compilers should. I should word my things. Most people working on compilers should think about this. But people who are just doing it for a hobby, for fun, to explore things, I don't think really need to care about performance to that level. And so the recursive enum structure is great. If you really care about performance, you need to deal with a lot more flat structures that are manually allocated in smart ways to keep the data densely packed and whatnot. Andrew Kelly's talk on Zig compiler performance updates and some of the data-oriented design stuff that they did really showcases this and how much performance you can gain when you really care. And when you really care, it's a lot harder to use like a Rust-style enum just directly. And so like lots of trade-offs in this. But my guess is like for a hobbyist, you know, pick whatever is going to make you like have something that's most fun and easiest to iterate on. And I think, you know, if you're making something that's relatively small, compiler times aren't going to be an issue. You know, I guess if you have a 300,000 line code base like Rock does, compile times will be a problem no matter the language, but a lot worse if you're using Rust. You know, but yeah, I definitely have a lot of opinions on all of this. Okay, what is this issue here? Oh, there's actually a bug for it. Theoretically fixed a while ago. We should have pulled in any fixes for this though. My guess for what's happening is because we're telling it to emit llvm-ir, it's probably not Zig that's emitting that's missing the call to floor. What's happening here is that Zig itself is emitting an llvm built-in for floor. And llvm, because it assumes C is the only thing in the universe, and that libc always exists, what will happen is that llvm will just go along and say, hey guys, I saw this built-in for floor, I'm gonna call libc, okay? I mean, you didn't say you had libc, but you know, I'm llvm and I'm, you know, built for C and C++ compiling, so I'm just gonna make the call to libc. And so that's probably what we're really hitting. But if it's added into their compiler RT, maybe I can just steal it from their compiler RT, and that would be even nicer than me needing to write it myself. I don't remember seeing a floor in here, but like I would gladly just, you know, we actually have stolen a solid bit of Zig's compiler RT. We just have their license thrown in there, and we use a good bit of it because they've already done the work of translating it to Zig. But because we deal with the final linking, we need to put it in Zig ourselves as opposed to how Zig does it. And so occasionally, oh, it's right there. Okay, cool. I'm gonna go to their main branch and make sure I grab a pulled up version of it. But I'm gonna just steal Zig's compiler RT floor, and that will solve this issue for everybody permanently. I'll probably have to do this for a number of their other math operators. But yeah, we've basically been doing this on a one-by-one basis. As we hit the need for certain functions, we kind of just come to Zig's compiler RT, and we thank them graciously that they ported compiler RT to Zig. It's actually a pretty great solution, but like if I come back over to this Rock implementation here, zoom in another notch. I'll come through here. If we go into crates, so our compiler is pretty big. In our built-ins, we have this bitcode. This is all of the Zig, the underlying Zig of Rock's standard library. Yeah, exactly. llvm sees the call to floor and helpfully replaces it with a call to libc, even though Zig just kind of said it's a floor built-in. Yes, that is pretty much what llvm does. The other thing that's a pain, I wrote an implementation of memcopy in Zig, and llvm happily took one of the loops in that and replaced it with a call to memcopy as an optimization. And so now I had a broken recursive memcopy. So, yeah, llvm's optimizations can be problematic sometime. But anyways, if we go into here in our source, we literally just have compiler RT here, and we've just kind of one by one taken functions that we needed. Yeah, you know that pain of llvm just replacing a for loop or something with memcopy when you really wanted your own implementation. But I think if I recall, so if you look at our, where is that? So we have our own versions of memcopy. We use both the Folly memcopy and the Muscle one, depending on exactly what system you're on and what's supported. But as a fallback, we have our own Zig version of memcopy that should be somewhere. There it is. that was ported from the C version that they had. But in this fallback memcopy, I forget what I had to change, but I had to change something to stop llvm from making a recursive call to this function in this function, right? I think what I ended up doing, I think it was at the bottom here somewhere. I ended up writing this comp time unrolling of the for loops. Like there were supposed to be a couple of for loops here, I think, and I just comp time unrolled them so that llvm wouldn't turn them into little mini memcopy calls, which is fine in this case because they're really short loops and they should be unrolled anyways. But like it's hard to deal with llvm sometimes. It has a lot of baked-in assumptions. I mean, even Chris Lantner and the team over at Modular working on Mojo are trying to wrangle LVM. They're like trying to use as little, like they're trying to like box it off and make it just compile functions and do things like how it's not even meant to do it, because using LLVM directly in a JITted language is way too slow. But they want to use it, and so instead they want to use it like a function at a time, and they want to restrict it a ton, and they want to port a bunch of passes so that they can do it differently. And so like there's a ton of stuff that they mentioned in a talk on about LLVM and how they're using it. That's basically like, yeah, we're trying to basically chop up and use as little of LLVM as possible in these specific places where it just does code gen, because we really don't want it to do all these other things because they cause problems. And like, it makes sense. LLVM's old. LLVM was designed to be a C and C++ compiler. It was not designed to be a modular compiler. It just happened to be designed in a way that worked out to be modular. And so of course it hits problems. But yeah, on that note, I still need to like implement memcopy for like, like find a fast memcopy for ARM and stuff. Because right now the ARM always just uses the fallback. But we basically have like if you have standard like AVX and everything memcopy, then we have versions for if you don't have the fancy stuff, and then we have a just Zig built-in fallback. I actually wonder, the Zig built-in fallback might be faster than this. I should do some testing. But yeah, we have a lot of weird stuff embedded here because we want Rock to be self-contained. And it's currently missing floor, which is why that doesn't work. It's the silly, simple things that you're like, wait a minute. Like, the compiler doesn't know how to generate a call to floor, but floor is a built-in. It just assumes libc exists and expects to call libc's floor. It's like, that is not the definition of a built-in. That is very much external, but okay. And so all of those things that it expects to exist, we have to replace somewhere. And so, you know, I guess I'll be throwing floor in here later today. I'll be just going down that Zig path. I guess I can literally just do that now, real quick. If we have... let's just pull this in. I need to do it anyways to get this mixed finally built. Okay, so it was in compiler RT somewhere, I think. Because I thought I didn't see it here in this version. Oh no, it's literally right. Well, that's floor. Oh, it probably includes floorf in it. That's probably why I'm confused. Oh, they literally just ported it from muscle too. Look at that. They literally just did the exact same thing as like I was gonna do, is port it from muscle. I think I'm just not gonna worry about it too much. And what I'm gonna do is we're gonna go here. First, we're gonna make a new directory for all of the sub-compiler RT things. Where is that? Like crates, compiler, built-ins, bitcode, source. What a long path. Yeah, and I want to make a compiler RT folder because all of our compiler RT stuff was embedded into one file before, but I know it's going to grow to a case where we need some of it not embedded. Oh shoot, is it undercase or upper or underscore or dash? Real questions of life. They use underscore, I'll use underscore. That sounds good. Okay. Anyways, and then what we're gonna do, we'll just go ahead and copy this. This is why open source licenses are amazing. We just keep the train of ported and copied things, and you know, we have Zig's license in here, so we are properly referencing them and whatnot. Oh, that's not how you spell compiler. It's crates first, that's why. Built-ins, bitcode, source, compiler RT, floor.zig. Okay, so now we have this floor here. Oh no, it depends on common. Oh, that's just for panic. We probably want to use rock panic anyways. I'll probably have to clean that up. What's the next thing? Yeah, if they just depend on it for panic, I can just get rid of that. Oh yeah, and they do linking different than we do for what we export, so I'll have to change that too. If we open our compiler RT .zig, real quick, let me go to main.zig as well. Yeah, so we do this as the comtime like import thing. So we'll just throw this in here as well, and make this import compiler RT / floor.zig. There we go. There we go. Okay. And so now that'll pull in our new thing. And what do we normally do? We do just weak linkage always, because if it exists for some reason, we will just take whatever the system feeds us. But if not, we'll do other things, and we don't care about the visibility. Oh shoot, that's not what I wanted to do. Ugh. So this is what .weak. Ah, that's not what I wanted to do. Tapping wrong keys, whatever. That'll work enough. I'll have to jump around again. Let me just do that. Okay. Have to be at the beginning of the word. That was a terrible fail at writing a macro. That's okay. It gets the job done enough. Okay. So we'll do that. We don't actually need all of these. I don't think we care about PowerPC, so I'm just gonna comment that one out for now. It's not a problem for us. Really doesn't matter if we export extra symbols. They will get cleaned up. And then the only other thing is that used a panic call, I think? No? It totally imported a panic. Real quick, let me go back to the source here. Yeah, const panic equals common.panic. So it just imported it, but never used it? Weird. Okay. Anyways, we don't need the PowerPC one. We theoretically just need floor F for now, but I will leave in the others for now, I think. What did I change here? Oh, I threw in that random thing. That's not needed. Oh, and then the other thing I want to change, I saw something. Let's see if I can find it. Where we misspelled dictionary. There it is. Okay, fix that real quick. But if I did that right, that should be all that's needed to add in all of those extra symbols here. And that will get us a working version of floor F that gets exported in a way that we shouldn't hit this issue anymore. So as long as the built-ins build, we should be good. Let's just see. I don't know why I did a release build. That's going to just make things slower, but whatever. We're here now. Let's see. Built-ins generally explode pretty quick if I did something wrong, so at least they're a pretty fast feedback loop. But otherwise, assuming that works, we should now have floor fixed. We just have to do that for all the other random symbols that llvm assumes libc exists for. But yeah, the Zig folks are awesome, and I'm so glad they ported compiler RT and a bunch of libc into Zig, because it just enables us to do so much more. I'm a little confused why we can't just like make them emit compiler RT. Actually, we might be able to do that now. It's supposed to work, but it was broken. But anyways, that Zig compiled just fine. Real quick, let me look at that again. We go to build here, and we go... we just search compiler RT? No? Oh, it's going to be on one of the build steps. So if we do like add object, I guess. I'm going to add object here. We go to a compile step. Yeah. Can we tell a compiler step to emit compile? Yeah, there's bundle compiler RT, which I swear I've used before, but it just doesn't, it never worked for us. I wonder if it works now though, because if it does, we can rip out this compiler RT and just directly use their stuff, which would be much nicer than me manually porting it. Let me try that real quick again and see if that works actually. So I guess I'll first commit just this of trying to bundle compiler RT again.
We also have to do that down here. So let's just build rock right off the bat. If our standard library builds, then it found floor, except I'm on, that's the other thing. Some of this only happens to be issues on certain machines. Like I think this is only an issue on Linux. Oh, look at that, collisions with names. I think it's actually bundling correctly. That would be really awesome. So real quick, let me go into main here and just stop using compiler RT real quick. Was it just issues with floor? No, it was issues with a bunch of other symbols. I think their bundling of compiler RT may be fixed. The question is if it bundles it when emitting llvmir. That's the important thing for us. We need it bundled there too. What are we hitting here? Oh, they even bundled their memcopy implementation. Okay. So assuming that they actually ported a good memcopy implementation, let me go here. I think libc currently just imports memcopy for us. Can we do this? Does this just work? I probably have to remove that comp time block. Zig's gonna complain at me if I just have an empty comp time block. I'm almost certain. Okay. Let's see. I will be very happy if this just works and then it also passes in CI. Because I know in past it didn't work. But given we're hitting those issues with defined symbols, that suggests it does work, which would make me very happy because we will get all the symbols we could possibly need for free, without needing to manually port them all over to Rock for no real reason. My matcha is exceptionally cold, but still tastes good. Only our compiler compiled faster. I shouldn't have ran with the release flag. It's totally partially my fault here. I should have just done a dev build. But at this point, I think the release build will finish faster than my dev build would have. So mono is one of the worst offenders we have because it does this fun thing called Rust macros. Lots of them. I'm pretty sure mono does a bunch of macros. It actually might be one of like the mono internal crates or something. Okay, but that compiles fine. And if I do like, I think the REPLs should hit issues if we don't link compiler RT. Like if I just do num.floor 27.7. Okay, the dev backend doesn't have it implemented. That's a separate issue. That doesn't help me debug things. We kind of switched the REPL over to the dev backend a little bit prematurely. It's kind of missing a number of low levels, built-in pieces, essentially. Like can be seen here. It's literally like a one-line add to fix that. And so like it's just someone needs to go through and add the one line for each different built-in. Like, or okay, it's maybe like 3 line, but like if I go just to show this, gen dev. If anybody ever wants to contribute to Rock, this is like one of the easiest things to do. We go with low level here. Just search that and follow it down. Nope, this is calling a low level. It's going to be in this function. Build run low level, I'm pretty sure. Oh, come on, Rust. Why is your language server not ready yet? Okay. Here we go. Now the language server is going to catch up and it's going to jump me to the wrong spot. But here's literally all it ends up being is like, okay, these aren't good examples. Where are some of the ones that actually call a function? Yeah, here you go. So this is one that actually calls a function, a cosine, because we're not going through the effort of implementing that in our dev backend. And so literally all it is if you see cosine, build a function call to the Zig built-in for cosine. That's going to be the same thing for floor. And so it literally will be, you know, to fix floor here will literally just be, if you see floor, you know, build a function call to floor. Oh, I guess you have to check the type. I guess we have floor as 2 different things. But like, it's, you know, check the type if it's F32 or F64 and literally just build function call to floor whatever. Like that's it. It's real darn simple. In fact, like if I do this right now, that would be enough to get the built-in at least kind of working. Oh, I guess it's already a string, maybe. Yeah, there we go. No? What do you want from me? What type is this? Expected string, found intrinsic name. What? Oh, what's wrong with converting it to a string then? What's the difference between this and this one? What am I missing here? These are all intrinsic names. Whatever. But anyways, there are other examples farther down, and so like it's a pretty simple thing to add all these missing built-ins to the dev backend. Some of them are a little bit more complicated, right? Like, so some of these are actually going to jump and we're going to generate the raw assembly. But for anything complicated, we just call a bitcode function, and Floor is complicated enough that we just call it bitcode function. And so that's just kind of how it works for us. Anything kind of complicated, the dev backend just defers to Zig. And so it's a pretty easy fix for a lot of those things. Anyways, I guess I'm actually kind of excited to try this, of like bundling compiler RT again instead of us manually doing all of our own wrapping. I'm really interested to see if this passes in CI. I actually probably can test this locally. I just need to get on my other machine. So because this is a macOS machine, so it doesn't use the surgical linker, which is what's causing the problem. So let's just add that little part of bundling compiler RT. Don't need that. Yes, we need to comment that out. Yes, we need to go back to the correct math.floor, and sure, we'll include that typo. So we'll just change this and we'll say through Zig. We'll push that up. Cool. And then if I just quickly SSH over to my other machine, that's a Linux machine here, not to the dictionary benchmarks. Oh no, this is the right branch. Be careful. Let's see. Fetch. Am I safe to just just pull, or do I need to do something else? God, I have so much random crap in this. What does it say? Okay, I'm just behind one commit, and it's safe to just git pull. I often screw myself up because I need to stash those changes. Actually, I could just remove them. Yeah, we'll just remove the changes I have locally. They're just like getting extra debug info. They're not important right now. Oh, it's gonna remove the Nix version of perf from my system. That's fine. Okay. Now that we have this here, I should be able to run whatever that failing test was that I tried to have a link to. So you checked, and it turns out what you did was just switch to GCC for that project instead. I have an LLVM issue. What do I do? Switch to GCC. I approve. There you go. That's how you fix all of LLVM's problems. You know, I've never actually looked at the internals of GCC at all. I'm assuming it's just as bad as LLVM, but I have no idea. I've like never actually dug through it, but like it's even older than LLVM, and it was written in a less extensible way to my understanding. But I don't know if that's a fair statement. That's just my rough understanding, but I have only lived in the world of LLVM and MLIR and etc. And so I don't have like a true knowledge around this. Okay, anyways, if I go back to, where is my pull request? Let me see what test failed so I can just run that on my machine to see if it still fails. That would have been this one here. On Linux, yes. They were running all tests, but, oh, it's just CLI running and stuff. Okay, yeah, we can do that. Cargo run. No, sorry, cargo test. Rock CLI. I probably want to run this with release. It'll take a minute. But if I don't run it with release, it might be, like the apps might just run really slow, and that's its own separate problem. Hopefully, Zig now bundles compiler RT such that it's pulled into the LLVMIR, because that was our problem before. Is it would bundle it in object files, but it wouldn't bundle it in LLVMIR, and we consume Zig through LLVM bitcode technically, and that's so that LLVM can then take the Zig bitcode, take the Rock bitcode, compile it together, and do cross built-in optimizations, and that's extremely important for our use case. And so for us. Excuse me. For us, that is like one of the fundamental pieces for why we use Zig, actually. Is we're able to get it to consistently generate nice LLVMIR that we can consume. Technically, we could try using Clang and do C, or we could use Rust. We actually originally used Rust for our built-ins because the compiler was in Rust. Why wouldn't you write the built-ins in Rust? And what we found is that Rust doesn't really help you here because all of the built-ins are basically just 100% unsafe code. And so if you're just 100% unsafe code, like what's the point of using Rust? It just doesn't really afford you much. Versus using Zig, it's actually really convenient to write 100% unsafe code. Right? It has those extra pointer checks and a little bit of type system stuff that's convenient. It has something that's very slimmed down and made for this type of an experience. And so for us, we found that we had a much better experience once we switched the built-ins over to Zig, and we're just essentially doing that all the time. And so I think that was one of like my favorite decisions that we did. Eventually I might have to port the dictionary to Zig if we can't get it performant enough in Rock itself. But my hope is that I can get essentially C-level performance or C++ level performance in Rock for the dictionary, though while doing a little bit of things that Rock can't normally do. You know, some cheats like saying, hey, Rock, don't check that we're actually safe and are within the length of this list. Just skip that check, right? There are certain things that I will get ability to do because I'm using working on the built-in like standard library, and standard library is allowed to skip a few things that regular users can't for safety reasons. And so like I'm hoping that I can catch up with the C++ implementation's performance in Rock, or at least be very close to it. And if not, I'll give up at some point and we'll just port it all over to Zig, and we'll accept, you know, Rock is really trying to be as fast as it can be while being a memory managed language. And that just has restrictions. And so like, we'll see how that goes. I'm very helpful. Anyways, these tests are all passing. I haven't seen anything explode yet. So that suggests that we can just use Zig's built-in compiler RT now. It generates what we want it to. So I'm going to go and just nuke all of our copy of compiler RT, and I will be very happy it's gone. Do I want to use their built-in memcopy though is an important question. Let me make sure that I'm sure they picked a good compiler RT memcopy. Like there's no way they did a bad implementation of memcopy here, right? We're Zig. I hope not. What do they have? Oh no, they have a bad implementation of memcopy. No, it's gonna make a rep move. They have an okay implementation of memcopy. I wouldn't call it a good implementation. Man. What do I want to do here? Do we just use their fallback memcopy? Do we... Like, it greatly simplifies a lot of the stuff we have to deal with if I just use Zig's memcopy here. And this is an okay memcopy, and llvm should admit a rep move for it on x86, which is kind of fast. It's not as fast as it can be, though. And llvm should also try to auto-vectorize it, which will be kind of fast, but again, not as fast as it can be. If you look at any of the major standard libraries, so like, this is probably not worth diving into right now. Actually, let me do this a different way. If I go back to the Rock source code here. Okay, cool, those all pass. Let me go back to the source code here. If we go to memcopy, and we go into... So this is just the muscle memcopy ported, and you can see it's already more complicated. It's doing a lot of tricks to try and elide cases that are common that are very short. Because the real cost of memcopy is twofold. Either you have short data, and you just wasted your time using memcopy. You shouldn't have used a memcopy. It was a waste. Or you have really freaking long data, and you need to have very optimized like SSE and SIMD instructions to make it work correctly. And Intel CPUs have tried to fix this with like a magic instruction that's supposed to auto-generate for this. And one day that instruction probably will actually work well. But currently it's hit or miss on how performant it is. That said, I'm still not sold. Like, it might still be worth using their memcopy. But you can see we actually use the Facebook memcopy. On x86 machines right now, we literally generate a call to this raw assembly, which is Facebook's implementation of memcopy. It is manually hand vectorized to make sure it was done correctly. I guess I have to test some more things. I have to see what the cost is of switching to a auto-generated memcopy over these. Assuming the cost isn't too high, honestly, it's probably worth just using Zig's memcopy. But I'm not sure what the cost will actually end up being. And so that's why we pull in hand-rolled memcopy and whatnot. And like if you were to look at glibc, which was the other thing that I was gonna pull up, like this isn't the real memcopy. This is gonna be like a wrapper, I'm almost certain. Let's see. Let's see, is this a real memcopy? Okay, so this is, yeah, not a real memcopy really. I mean it is, but it's just 3 macros. That's actually kind of funny. I wonder if this is actually implemented in C, because I know a lot of different things, they tend to implement this type of stuff directly in assembly, right? So you can see these different folders where this is the generic folder, then the i386 and the PowerPC. So that suggests that only on old 32-bit machines and on PowerPC do they actually use that memcopy probably. They probably have custom assembly somewhere else for memcopy. And that's because specific implementations are very important for this type of stuff. Because memcopy can literally be most of your execution time depending on what you're doing. We hope not. We hope you're not copying too much, but it is one of the very common, very expensive costs. And you can see what they do is they basically align to a page, copy and page size things, and then copy and word size things, right? And so they basically start super tiny to get their alignment right. Then they go to as big as they can, and then they kind of shrink down a little bit from that, and then they do the final little bit at the end. But actually, most of the time, they're going to be like, oh, actually, your memcopy was too small, and they're just going to do the last little bit at the end. Memcopy is a hard thing to fine-tune correctly. But I don't know. Maybe we should still use the Zig version. I guess I have to be careful. If we use the Zig version, there's a chance that it generates a recursive memcopy when we run more optimizations on it, but we'll have to look at that. Okay. I guess for now, I'm going to assume I'll be removing this, but I will make I will later run some benchmarks just to make sure there's no major performance regressions of any sort. But for now, I'm just going to assume that my PR can depend on Zig generating all of this. Builtins, bitcode, and so that means we literally can destroy 2 things here. So we can get rid of compiler RT, compiler RT.zig, libc, c.zig, and libc. So like that greatly simplifies what we actually have to care about built-in wise, assuming this is like a valid thing to do. So I definitely want to try it and see if it, passes our CI and doesn't hit any weird issues. Because it definitely is much simpler for us if we can just depend on their compiler RT. And one day they may do some certain hand optimizations if people find it a big enough problem, right? Let me remove these flame graphs before I actually commit them. Okay, so the only actually modified file is... do you think all the features of a language should be designed up front or solely added on later? I think if you are a hobbyist and you have an idea for a language, there's 2 cases. Okay, one, if you're just doing learning, just mess around. Start with like something like monkeylang from the interpreter book, or LOX, I think, right? Start with something like that if you're a hobbyist. Build off of that. But then the bigger thing is, if you're actually trying to design like a language that you want more people to use, or if you want to give yourself more of a challenge and you're really trying to learn and whatnot, I think you want to get a solid basis of like the selling points of the language, the core features, the core ideas, be able to write out a few examples of it, like really understand it. I think that's important because you don't want to paint yourself into a corner in your implementation. And so I do think that a lot of the core stuff needs to be designed up front, but like Rock is changing pretty significantly at certain points, but like the core of Rock is not. Your ideas feel like unsafe Rust currently. Now you want generics and pattern matching, and it's probably too hard. Yeah, generics and pattern matching are both quite complicated to implement. I mean, I guess it depends on what you're working on, right? Are you working on a compiler or an interpreter? Fundamentally, how is your language working? And then in general, you know, even just parsing pattern matching and making sure that's correct can be quite hard. I personally don't do much work with our parser. I need to do some work with our parser for one of the features I want to add. And I'm not looking forward to it because it's a big nest of parser combinators. And for a lot of people, that's beautiful and they love it. But for me, it's just discombobulating. And so, like, you know, I'm sure some of our code makes a lot of sense, especially when it comes to the fancy error handling. But yeah, if you're making a manually memory managed language that's compiled, so you're making something that's similar to C or Zig or whatever that's trying to be pretty simple, but you want a few extra features, that definitely is a harder area to work on. Yeah, I mean, you may not be able to come up with anything unique when there's Zig, Odin, Jive, Rust, etc. Like, that's totally fine. Like, it's fine to make your own version of C. Like, that is a great learning experience, and it's valuable still, right? It may not be something that's ever, like, really shared wider or that the people tend to use in any major way. But, like, I do think that, like, you know, you don't need to make something that's super unique. Learning to implement something like Zig is very hard. Excuse me. You know, like, if I had to go through and implement a compiler from scratch for Zig, you know, they literally print out the grammar for you. And I think I would have a hard time doing a compiler for Zig. And that's with the fact that I work on Rock. I writ the core of our entire dev backend. You know, I think I'd do much better at the tail end of the compiler than at the front end and whatnot. And so, like, even for someone like me who's done a lot with compilers, I think that would be hard. And I think that's where there is some merit in certain tools like MLIR or certain tools like certain ways of really building nice ASTs that are just like the generic style nested expression enums, right? Those type of tools tend to be a lot more flexible, right? They help you just kind of like parse things one little piece at a time and make this giant nested structure. And sure, that might not be the most performant, but it's way easier to work with. And so that's why, like, Rust enums, I think, are extremely helpful for this type of stuff. That said, compiling generics is actually just like a hard problem. Hard problem might not be quite the right term, right? It's not like a true, like, hard, empty hard or whatever problem. But, like, fundamentally, when it comes to compiling generics, what you end up dealing with is that you have to basically pipeline a type through a definition and then figure out a lot of things based on that, right? And the type might have extra compile time stuff that you have to decide. But I would say pattern matching also, like, it's not easy to parse. So, like, those are, like, just harder problems. I think generics and pattern matching are probably some of the harder problems for hobby programmers to get into. So definitely, if you manage to figure it out, that will be a step that most hobby programmers never figure out, right? The closest thing most hobby programmers get to if they're working on compilers or interpreters that's generic-like is just your Python object, right? This can contain anything in it, but that's not a generic. That's not a compiled, you know, monomorphized generic, which is a much harder thing. I guess the best statement for generics is build an AST for your function that kind of has, like, blanks in it, and then every time you call that function, check for the blank and fill in the correct blank, essentially, is what you're doing. And so I think that's not too hard to do, right? And the parsing generally isn't too complicated either. And then you just make a cache of those functions and say, oh yes, I have already built that version of this function. And so you can kind of just do generics on the fly in that matter. And you can do that at any level, right? You could do that way up high in your compiler right after parsing, or you could do that right before CodeGen, or even like during CodeGen. You could stamp out all these templates. But I think that's the best way to think of generics, is kind of like making templates and stamping them out, right? And then the other thing is pattern matching, which I just think is really hard for parsing. I don't think it's really hard otherwise. You know, once you've parsed it, it's mostly just kind of do a bunch of ifs and grab different data and check it, right? I guess if you're doing like exhaustiveness checking in your pattern matching, that's a bit complicated. The hardest decision is deciding which features I want. Yeah, this is why I love Richard. See, in the Rock world, Richard has this vision, and it's a small, clean, simple language. And so most features, the answer is just no. I mean, we talk about them and we discuss and we dig into details, and I've convinced him to add some features and whatnot. And I don't remember who had the idea of backpassing in its current syntax. I remember when all that discussion happened before it existed. And man, am I glad we have backpassing. And so features do get added and things do shift. But like Richard came with this idea, and it's this core, simple kernel of an idea, and it helps just cut away so many different things. I think if I were to design my own language, I would just give up and I'd make Zig. And I'd tweak like 1 or 2 things because I don't want to deal with figuring out and designing things. Yeah. I do think functional languages try to be more elegant. I think it's just the mathematical background and the purity that make them seem more elegant. I guess they tend to also have certain helper wrapper functions that you don't find in other languages. Huh, that's a good point in pattern matching, right? Yeah, you can go look at the Elm implementation or the Rust implementation. And so like it's a lot easier to dig through and figure out. Oh, there are old PDFs and things from OCaml still with comments in French. I like that. Now, of course, to go through the Elm implementation assumes that you can at all read Haskell, if I understand correctly. So that may not be the easiest task. But yes, that's true. It's like now starting to appear in like every language, so that may not be too bad to add anymore. I guess, Fulkert, since you're here, any chance you have any comments on if like nuking memcopy and just using the Zig compiler RT1, you think that'll be fast? Fast enough? Because we can finally nuke all of compiler RT that we've copied in here, but it also comes with a memcopy that may not be as performant, but I don't actually know what it'll compile to. But I guess I'm going to try it. I should probably run this and make sure that we still compile. I didn't blow anything up. Yeah, I think, at least based on looking at the implementation, it seems like a really direct, naive implementation right now, but I'm assuming that if we chat with Andrew about it and we say that it's actually a performance problem, they'd look at making a fancier implementation. But I think right now it's literally like, I just had the source up. Unless there's somewhere else that they have another part of the source, it's like the ultra simple implementation. And it's basically saying, hey, compiler, generate for me whatever you'd like as an implementation. But yeah, so I don't know. Like this one is literally just like saying, compiler, please generate whatever the heck you want. And get taken down by the Rust Foundation. Rust Foundation after everybody. And the compiler reach Rust. You know, the more I work with llvm, the less I trust it. I'm just going to be honest here. It does so much magic, and it is wonderful, but man, it's a struggle. I really want something new. I want a new replacement for llvm, but it doesn't exist yet. There are people working on it. What was the one I saw recently? The one that the Odin team is working with somebody who's building his own compiler backend to compete with llvm. I don't know if I'm gonna find this. I don't really know what to look for, because I just think the Odin creator just like sent out a tweet about it. That's not what I wanted to put there. Odin Lang. But I forget what it's called. So, okay, so the big problem with llvm is that it assumes everything's C, and you have to make your language C for it to optimize it correctly. That's fundamentally the biggest problem with llvm. And that's really, I think, the biggest reason why I want something else. I do think on top of that, llvm is given up on performance, like in terms of compiled time, and I think there's a better like middle trade-off somewhere. But those are, I think, the two biggest issues. On top of that, it's unable to think about a lot of certain like memory things and other optimizations because of the C lens onto everything. And so I do think there's a lot of gaps where it just doesn't have the optimizations built in or the ideas for it. Wasm time. Oh man. compile to WASM and use WASM time to compile to machine code. That's obviously the solution. Everything should be WASM now, even native stuff. Okay, cool. This compiled. I'm gonna just send this, and it's, I think, probably the better idea. Not Rust bitcode, Zig bitcode. But yeah, it at least simplifies stuff for us. Let's see. Oh yeah, I think crane lift's a good idea. I'm just so confused by it. Like it seemed like it was about to be a thing. Like it was getting talked about, I feel like, so much in, I don't know, 2019. I thought it was about to be this big thing that everybody was going to use or something. Or at least Rust was going to use. And then I feel like all of the energy behind it seems to have fizzled out from my perspective. And I just probably am in the wrong communities for this. But like it just kind of like went poof from my perspective, like out of public view. But yeah, I do think crane lift would be a good one, assuming it is actually written rel. I haven't dug into it at all. But given that it's a modern compiler being written by... Was it originally worked on by the Rust... Like, the Rust folks, were they the original ones working on it? Or is it that someone else was working on it and they just wanted to adopt it? Do you know? Also, suffering with linking is something I believe in strongly. I'm still scarred from my times working on a linker, and the linker still doesn't fully work. But Rock uses it, so it's, you know, it's kind of in production. It's a source of bugs for sure, but fundamentally the core of it works and it's awesome. Okay. WASM time is the group that drove it. That makes sense. Okay. I didn't realize that. That makes a lot of sense. So it's out of the WebAssembly folks, where you want like a middle ground of like, I need to do some sort of JITting compiled optimizations. And this is also where JITted languages can be kind of magical at times too, I guess, to be fair, right? With a JITted language, you can compile one function at a time, and then if you realize you need to, you can do the inlining and compile the inlined version of some combined function. And so then you can like hide a lot of the compile times. Okay, the person who wants to put in Rust is just doing it because they want to do it. Okay, that makes sense why it kind of had a bunch of energy for like a little bit and then kind of seems to have disappeared from that community. It's just not a paid focus and whatnot. Yeah, I don't want to think about how much time is spent every day compiling code through llvm and GCC and whatnot. Like, it's like the amount of server effort that goes into like Google's compilation flow is, I'm sure, terrifying. I know I've seen a number at some point, but I don't remember it anymore. And I don't have access to it anymore, so I wouldn't be able to look it up. But, yeah, compilers are hard. Who would have guessed? Oh, interesting. Benchmarks are kind of math from the compile time perspective. Yeah. I'm like, I feel like you can't, like, there has to be a way to do way better than what llvm does, because llvm fundamentally is like a bunch of classes and pointers and virtualization, and like, it is a stack of things that should be like the classic example of like pointer hell to some extent. And so like, I can't imagine that it's fast from that perspective either. Like, if you were to redesign llvm, you'd probably want to remove a lot of the pointers and virtual stuff and instead do things like Rust traits and monomorphization and things of that nature. And I think you should get some gains from that, but maybe there are functions that are at that pointer abstraction level are actually big enough that that doesn't really matter. I don't really know. I guess a lot of the passes, to be fair, are just stuck in hot loops, just scanning IR and repeating things. I guess that's a thing I don't know. I'm assuming is there IR densely packed in something currently for llvm? I haven't looked at that in a long time. Because if that's densely packed, then I guess it wouldn't be that bad. But with MLIR, I think everything is allocated in like one ginormous arena that just never frees its memory, essentially. I'd assume llvm probably does something similar under the hood. I just haven't looked into those levels of details to llvm. Some people I work with are currently working on porting parts of llvm. I do not envy their work that much, though I have talked to them about some of it, and I kind of would be interested in trying some of it, just because it's always interesting. They get to do a lot of really fun performance optimizations and whatnot. Okay, let's see. Okay, anyways, CI is running on this. I decided just to fully remove compiler RT and let us pull this in, which I think should fix all of our linking issues, hopefully. That sounds pretty nice. So, like, a reasonable trade-off. Alright, anyways, I think this is probably a pretty good time to cut the stream. I need to at least do a little bit more work today, figure out some stuff, try to track down a bug I've been tracking down for 2 weeks. All the fun stuff of life. But thanks everybody for joining and chatting. It's been a fun time. Hopefully you guys got something interesting out of it, and when I upload it, hopefully more people can learn a thing or two. But I will chat with you all in the future and on Rock Sulip and whatnot.